Our next test is called the alternating series test, and after this one we only have two more. We have the ratio test and the root test, and then we're going to stop and we'll take a test on the tests. So I'm going to test you that you know how to test the tests. Anyway, the alternating series test is incredibly easy to spot, and that's nice because one of the more difficult things with series is looking at it, and they all kind of look the same, and what test do I use? But alternating series have a tell. And their tell is that they have to have what we call an alternator. And what an alternator does is it causes terms to go from positive to negative consecutively. So it goes plus, minus as you go down, or minus, plus, but it can't like go plus, minus. They must go consecutively. And there's the most common alternator. We have what I call a sneaky alternator, but the most common thing to cause that change is -1 to a power of n. And when you're deciding what power of n it is, remember the first count has to generate the first term. So I couldn't have done -1 just to the nth on this one because -1 to the first is negative, and I know I need to start at a +1. So I chose -1 to the n plus 1. Could I have chosen -1 to the n plus 3? Well, if it generates those terms, yes, I could. So on this one, you'll notice my alternator is what I call it, is -1 to the nth, but that's because when I put in a 1, -1 to the first is negative. And so alternating series have a big tell, and that's that -1 to some power, and you can see it. And if a series is alternating, we have a really slick test for convergence. And what we do is we take the limit of the series in the absence of the alternator. So what we do is we take that alternator away. Kind of basically, some texts will say take the absolute value of a sub n. If you consider a sub n this entire term, then sometimes you'll see absolute value there. But what we do is we remove that alternator and we look at the series without it. And if that series has a limit that goes to 0, then the series with the alternator will converge. Now, I just said a whole bunch of words, and I want to make sure that that makes sense to you. What that means is I'm going to take the most common divergent series, the divergent harmonic. And we've proven a couple of ways that that does truly diverge. It's our fence for divergence. And when I take its limit, the limit goes to 0, but the series diverges. So again, I want to stress that again. Just because your limit goes to 0 does not mean a series converges. The nth term test is for divergence only. So if I take the limit and I get something that's not equal to 0, what that means is I'm going to eventually just keep adding the same constant. Like if my limit goes to 2, with that series, I'm going to keep going +2, +2, +2, and the sum, or the series, will diverge. If the limit goes to 0, then that nth term test is inconclusive. However, when I put this exact same series in the presence of an alternator, and let me write out what that series would look like. Instead of being without the alternator 1 plus 1/2 plus 1/3 plus 1/4, which I know diverges, when I put in the alternator, I get 1, and then I'd get, when n is 1, I get -1 to the second, which is 1, and when n is 2, I'm going to get -1 to the third, which would be minus, and then I'm going to have, plus, and then minus. What happens when I put in that alternator is I end up subtracting every other term. And what the alternating series test says is that if the limit, let me show you this one. If the limit of a sub n, or the absolute value of this chunk, basically remove the alternator, goes to 0, then the negatives are enough to make the series converge. So that subtraction causes enough to be removed from the sum for us to truly say that it converges. So it's kind of like the nth term test. However, this is for convergence only, and it needs to have the presence of an alternator. So, and it also says, by the way, if you take that limit and the series diverges, we say it diverges by the nth term test, not the alternating series test. Now, that's kind of confusing. So I'm going to put a little, where do I want to put this? I think I have it on the next page. So, no, I'm going to put a little series of steps here. Series, that was a pun. Not as in like a mathematical series, but a list of consecutive steps. So what do we do with the alternating series test? I'm going to put this down. If you see an alternator, and what is an alternator? -1 to some power. Maybe it's n plus 2, n plus 1. By the way, -1 to the 2n is not an alternator. So be careful with that, because -1 to the 2n, right, is going to be 1 for all n. It won't cause alternating. But so make sure it truly is an alternator. But if you see an alternator, remove it. And we're going to see what happens to the function without the alternator. Take the limit as n approaches infinity of that series, or the nth term, without the alternator in it. If that limit goes to 0, then the series converges. It means that alternator was enough to make it converge. So it's very similar to the nth term test, but what this does is we say it converges by the alternating series test. Remember, when we get a limit that goes to 0, that does not mean that the series converges. But if it goes to the 0 in the presence of an alternator, then the series converges. So we're going to do these in reverse. Instead of going A, B, C, there's a reason. I don't like the order that these are in. We're going to go do letter F first. And it's one I already did. So when I see this alternator, what I do is I go, alternating series test, and I take the limit as n approaches infinity of the series without the alternator. So I do 1 over n. That limit goes to 0. So I would say, therefore, this series converges by the alternating series test. Really easy, but understand what that's saying. It's saying that putting that negative in there and making every other one cause subtraction from the sum is enough to make the series converge. Just because the limit goes to 0, again, does not mean a series converges. But in the presence of an alternator, it will. And you could go test that out on your calculator. It might be worth your time, so my words actually have some meat to them. But if you were to go math is 0, and if you were to do the sum n equals 1 to, say, 99 of this, I'm going to just call it a sub n, and then if you were going to go n equals 1 to 999 of a sub n, you'll see them being very, very, very close to each other, because they do converge with that alternator in it. But if you were to remove the alternator and just do 1 over n, we already have shown that that actually diverges. All right. A lot of words. It's actually an easy process, but I like you to understand what you're doing. So when I see this alternator, I remove it, and I take the limit as n approaches infinity of the series in the absence of the alternator. If in the absence of the alternator the limit goes to 0, then we can say that the series converges by the alternating series test. Done. Easy, huh? So again, in the presence of an alternator, if the limit as n approaches infinity of the series in the absence of the alternator goes to 0, which this one does, then the series with the alternator in it will converge by the alternating series test. And that's important that you put by the alternating series test because, again, just because a series goes to 0, its limit of the terms go to 0, that does not mean it converges. They have to go to 0 fast enough. And what I'm telling you is if it goes to 0 in the presence of an alternator, it'll make it go fast enough to converge. We're going to back up. Going in reverse here, huh? So let's go take a look at this one right here. Letter C. You might say, well, I don't see the alternator. This is what I like to call the sneaky alternator. I heard someone else call it that once, and I liked it. The sneaky alternator, because it's not in your face. But if you consider cosine n pi as n goes from 1 to infinity, when n is 1, it'd be cosine pi. When n is 2, it'd be cosine 2 pi. When n is 3, it'd be cosine 3 pi. When n is 4, it'd be cosine 4 pi, blah, 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 blah. So I do get an alternating series with cosine n pi. It acts exactly as -1 to the n over n. And again, I have to be careful that I generate a -1 first here, but I do, so I didn't need that n plus 1 on there, but those are identical sequences. So again, if I can show that the limit as n approaches infinity, when I remove the alternator, goes to 0. Now I know that series without the alternator diverges. But in the presence of the alternator, the every other term subtraction will cause the series to go to 0 fast enough to converge. And I've said that a lot, but I like you to, if you understand the theory behind the test instead of just trying to memorize tests, it really does help. So because that limit goes to 0, in the presence of an alternator, we would say therefore S converges by the alternating series test. It's a very, very easy test to run. Now let's go take a look at this one. I see an obvious alternator. When I put in a 1, a 2, a 3, a 4, that's going to alternate from, it'll go negative first, it'll go negative, positive, negative, positive. So I remove the alternator. And if in its absence, the limit goes to 0, that series will converge. This one I would use maybe a little L'Hopital's rule on, because I'm not 100% convinced. This is a slow-growing function, so is this. Normally, natural log grows a lot slower than most anything, but I would still, just to make sure, unless you're 100% positive, use some more methods to be for sure. The derivative of n with respect to n is 1. The derivative of natural log would be 1 over 2n times the derivative of the guts, boom, 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 which equals n. So really, I'm taking the limit as n approaches infinity of n. This equals infinity. It does not equal 0. So what I know is S diverges, but not by the alternating series test. The alternating series test is a one-way test for convergence only. This diverges by the nth term test. So these are very similar tests. The nth term test and the alternating series test both start with taking a limit. The nth term test says that if your limit does not equal 0, the series diverges. If the limit equals 0, the nth term test is inconclusive. In the presence of an alternator, the alternating series test says now if your limit goes to 0, the series will converge because that subtraction of every other term will cause it to go to 0 fast enough to converge. So I've said it a lot, but it's important. So again, I see an alternator, dead ringer for taking a limit, which you should always do first anyway, because you should always run that nth term test first. So, and again, that -1 to the n plus 1 doesn't contribute anything to the magnitude. It contributes only to the sign of every term. So anyway, limit as n approaches infinity of n over 2n minus 1. I am removing the alternator, and I get 1/2. This does not equal 0. So I would say, therefore, S diverges. But again, not by the alternating series test. That is a one-way test for convergence only. All right. Therefore, S diverges by the nth term test. So when do we run the alternating series test? Every time we see an alternator. What does it say? If the limit goes to 0 in the presence of an alternator, you can say the series converges. If the limit goes to 0 in the absence of an alternator, like in a series that doesn't have an alternator in it, like that limit goes to 0, but there's no alternator. So the fact that my limit goes to 0 does not tell me that that converges. Okay, so we can only say it converges if it does so in the presence of an alternator. So next up, another kind of confusing topic, absolute versus conditional convergence. So now when the series converges and it's alternating, we're going to classify it as either absolutely convergent or conditionally convergent. And I think the formal definition is confusing. So I'm going to put it in a what does this mean box. And I'm just going to talk about it generally. So let's go take a look at letter F up here, one we already did, so I can explain it with that one. So you'll notice with letter F, when I removed the alternator, the limit as I approached infinity of 1 over n went to 0. So I'd said that therefore the series converges by the alternating series test, meaning that putting that alternator in there caused a formally divergent series to get to 0 fast enough to converge. So what we would say is because this series without the alternator is divergent, we would say that it's a conditionally convergent series. If in the absence of the alternator, the series converged anyway, then we say it's absolutely convergent. So let's get this down. I want to get these steps down. So what does this really mean? All right, here we go. When you see an alternating series, when you see an obviously alternating series, -1 to the n plus 1, whatever, like this. Or again, you could have your sneaky alternator, cosine n pi. By the way, sine n pi is not a sneaky alternator. You can give it a whirl. But when you see an obviously alternating series, and they're incredibly easy to spot, what do you do first? Number 1, you remove the alternator. Basically, you're taking the absolute value, and that's what this is kind of saying up here. But I just say remove that alternator. And when you do that, you're going to take the limit of the rule of sequence in the absence of the alternator. If you get 0, you say the series converges by the alternating series test. If you do not get 0, this would imply this series diverges, but not by the alternating series test, because that's a one-way test, by the nth term test for divergence. Okay, so once you've decided that it converges. You're now going to classify it as absolutely convergent or conditionally convergent. What that really means is, did it really even need the alternator? So what you're going to do is, you're going to next, again, look at the series as n approaches, as n goes from 1 to infinity without the alternator. So remove the alternator, and sometimes this will say absolute value of a sub n. So when you remove that alternator, does the series converge anyway? So if, let's call this S sub 2, if S sub 2 converges, no alternator necessary, then we say it was absolutely convergent. Whew. If S sub 2 diverges without that alternator, then we say that it was conditionally convergent. It sounds a lot harder than it is, simply because I'm really trying to make sure that it's all spelled out for you and not just in a formula, and that you understand it. So let's go do a couple of these, just two of them. It's nice and easy once you have all that background in it. So again, I look at these and I go, oh, it's got the tell for an alternating series, -1 to the n. They are going to have consecutive terms go from plus to minus, or vice versa. I want to determine whether it converges or diverges. That just means remove your alternator. So in the absence of the alternator, does that limit go to 0? Yes. So therefore, I say that S will converge. Not by the nth term test. The nth term test is a one-way test for divergence. S converges by the alternating series test. To determine whether it converges absolutely or conditionally, I remove the alternator and I look at the series in the absence of the alternator. In the absence of the alternator, this is a divergent P series, because P is less than 1. So because it needed the alternator to converge, we would then say that our series, our alternating series, is conditionally convergent. It needs the alternator to get it to 0 fast enough. If it doesn't need the alternator anyway, then we say it's absolutely. You don't even need the alternator to determine convergence. All right, so here we go in another one. Alternator, that's a tell. Remove it. Take the limit as n approaches infinity of the rule of sequence in the absence of the alternator. Did I get 0? Whoopsie. Yes, I did. What if I didn't get 0? Well then, it diverges by the nth term test for divergence. All right, this equals 0. So therefore, I can say that S converges by the alternating series test. A one-way test. You should never, again, I'm going to repeat it because it happened on the quiz. You should never, ever, ever say something diverges by alternating series test. You should never, ever, ever say something converges by the nth term test. They are both one-way streets. So this is telling me that this alternator will cause it to go to 0 fast enough to converge. Now I want to see if it would have gone there on its own. So now I look at the series in the absence of the alternator, and it still converges, okay? Which converges by the geometric series test. 1/3 is less than 1. So because it converges on its own and doesn't even need the alternator, we would say therefore S is absolutely convergent. Phew! It's an easy test in and of its own, but will you remember that when they're all mixed together? You will by next Friday because we have lots of time. Your assignment is 1 through 9 on worksheet 2D. Have a good one. Over and out. Peace out, Girl Scout. Don't do anything I wouldn't do.